Hello, fellow dorks. We're just gonna jump right into it. So, if you haven't seen You Make Me Skate's video on the foldable skateboard, go watch it because that's what we're talking about. We're talking about this. So I'm just gonna go through and talk about some of the points of this board that no one would ever know unless I told them. Starting with why I made this thing. I actually wanted to work for Chuck Hoberman. Chuck Hoberman is most known for the Hoberman sphere, the tiny little colorful injection molded toy that goes whoop whoop. And what's really cool about him is that he's done a lot more than that. He has done ginormous versions of that. He's done a lot of transformable design. And I really, really respect him for all the work that he's done. And I found out about him through a gift. So I was gifted the Hoberman Switch Pitch, which is kind of this unstable equilibrium toy, and this would be like maybe a ball at the top of the hill, the unstable equilibrium, and then you push it to one side or push it to the other, and it lands in different configurations. So it lands on, this is the one I reverse engineered and made, on this side or this side. And it got me really interested in what he was doing, what he did. And so I researched him, and I wanted to work for him. And so what I did was I recreated his portfolio to the best of my ability in hopes that at the end of it, I would maybe apply it to something new, or that would be good enough to just get a job for him. So after the Hoberman Switch Pitch, I wanted to figure out how his linkages worked. Through some linkage analyses, I discovered how they worked. And in order to prove it to myself and anyone else how they worked, I had to build solutions to them. And what he started with, as far as I'm concerned, as far as I know, is a ring. And this is my first ring. Now, some of you may see this and say, oh, that looks like the iris mechanism. Well, it is. The iris mechanism is what I would dub a symmetric Hoberman linkage system. And what I mean by that is all of these are symmetric. These are all essentially the same piece, except I have little stops, but whatever. They all are the same piece. And that's why this isn't enough proof to understanding or to showing understanding of the Hoberman linkages. But the basics of a Hoberman linkage are this. If you take a linkage, which is, this one is, well, here's 4-bar linkage, 4 pivot points, 4 bars, basics of linkages, and you draw a line from these 2 bolts to the center, and these 2 bolts to the center-ish, it's a little wobbly, you'll notice that as they collapse, they retain the same angle. So what I mean by that is, if you, again, draw the line from the center out, you'll see that those points lie on the same line out here as they do in here towards the center. And this is kind of the secret. This is the symmetric Hoberman linkage example. And what did he do next? What he did next was he created a collapsible geodesic dome. So I created a collapsible geodesic dome. And this is the first proof of concept of creating with Hoberman's linkages. So these see-through linkages are actually the symmetric Hoberman linkages. And they are because this length and this length and this length and this length are the same. And these angles are the same. And if you'll notice now, the way I drew a line in this planar space to the center of this circle, you do it in 3 dimensions from this one. So the normal of these nodes, so the line going through these nodes to the center of the sphere, stay on the same line as they collapse and open. You might be able to see that now that I've kind of depicted it. But the added feature to this guy are these white linkages. These are non-symmetric Hoberman linkages, which are crucial to making anything that is 3-dimensional. So you'll need same length between the non-symmetric and the symmetric Hoberman linkage joints, else you won't be able to open and close as much. And then the reason that they're not symmetric is because these lengths are different. Why are these lengths different? Well, because these lengths are different. So this length is actually different than this length. And that goes to Buckminster Fuller math, geodesic dome stuff. You can just get these values, essentially. But this length is different than this length in this 3V geodesic dome. And so then the compensation, if these have to be the same, are in this length here. So this was my first foldable geodesic dome. Hoberman himself has built many a large geodesic dome. And as far as I know, the largest one is 19 feet in diameter, and it hung in New York, in a New York museum. And it opens and closes. It's a big ball of aluminum. It's really cool. And here is mine. So this is engineering birch, 3D printed nodes, 1/4 screws, and it is 20 feet in diameter. And if you collapse it, it fits into my car. Volumetrically, it doesn't actually fit through the door. And then when you open it, my car fits in it. After this, I was pretty confident that I knew how to apply, I'll call the linkage math. And I wanted to apply it to something else, something cooler, something different. So I wanted to apply it to a skateboard. So I did. Here's the first version of the skateboard. 3D printed plastic, 1/4 screws again, laser cut acrylic linkages, and the goal is to make a metal one that opens and closes as smooth as this one. So what did I build next? Next I built the CNC. And this CNC built this first aluminum version. So this aluminum version has some problems. That being the main one, which is chalked up to tolerance stacking, and poor machining. So the tolerancing comes into play in a couple different places. First is the slot that the linkages fit into. The linkages aren't actually a 1/4 inch. They're not 250. They are 258 to 246, and I didn't really know. And the slots, I made them 20 thou big because I was like, sounds like a round number. So you have tolerancing this way, a ton of motion here. Then another huge area of tolerancing is this. The linkages have play because the ID hole that this screw goes through isn't mated to the cylinder that would be the screw. Because, first of all, the screw isn't a cylinder. It's got a bunch of threads through it, so you have a bunch of area that the linkages can actually move through. And then, on top of that, the holes weren't even properly sized. So you get this tolerance play right here. Another thing to note is that this is 2-ply. I'll just call it 2-ply, because there's 2 linkages per point. And a way to distribute the moment is to essentially make it longer. So if you had 2 linkages thicker, you would get less play. But I wasn't about to make linkages 3 times that long, and another way to achieve the same effect as distributing the moment, distributing the slop, is by doing 4-ply. So, yeah. And another way to fix the tolerancing is to make it a shoulder bolt. So I didn't know what a shoulder bolt was, and it's essentially a cylinder that you can fit through a precise hole, and there goes most of the slop anyways. So this version drilled reamed holes to plus or minus 2-3 thou, along with an undersized shoulder bolt of 1 thou, and now we have at maximum 4 thou play, and I can't even feel it. So the tolerancing between the linkages was crucial. The 4-ply-ness of the linkages also ridiculously crucial. It added so much stiffness, I just couldn't even believe it. Another thing is just to, go better and machine the nodes better. But we still have 2-ply here, and if you see, that's actually, you have some shifting, and that's actually where a lot of the shifting comes in. And so for the next version, I'll make this 4-ply. So we have the tolerancing issues that led to the more stiff board, but now when you ride this board, well, before when you rode this board, V1 of this board actually had some wobble, and it came from this. So we have the 2-ply nodes not giving enough support to the machined truck plate. So this is where you mount the truck to this. I call it the truck plate. So you have the truck plate that has wobble, and you would actually feel it in the board. You would step on it and you would hear, because every time you got up, the give would make the aluminum hit each other, and it felt awful, it sounded awful, so I needed to fix it. How do you fix it? Well, I actually ended up putting cammed linkages to take most of the load off when you were riding it. So as you open the board up, the cam for these linkages, so these linkages are different from everything else, push down on this truck plate and pretty much get rid of all the play. Huge step forward in the stiffness of the ride. But what did that cause? That caused a different problem. At the time that I created these linkages, the center spine was still only 2-ply, which means you had one shear point across the shoulder bolt. Insert video here of my friend riding it. He jumped a 2-stair and sheared a 17.4 pH shoulder bolt like it was nothing. I found the bolt later on the ground, and it looked like the surfaces had been machined. It was really kind of cool. And so then I knew I needed to make this center spine a 4-ply board. The center spine 4-ply. Not for structural reasons, because it took the weight of anyone riding it, but because it needed to distribute the shear across the bolt in 3 spots instead of 1. After that, the ride hasn't had any bent bolts or broken bolts yet. Wood dust. Another one of my favorite little things about the board that maybe you would see, maybe not, when you collapse it. I talked about earlier in the video about how this diameter is actually the limiting factor to the collapsibility. Well, that's actually not the case while I'm trying to maintain an almost perfect approximation of a skateboard, because these lengths, when they fold up, interfere with the nodes. So in order to get just maybe another inch of collapsibility, I dished out these linkages so that when it collapses, they kind of fit next to each other, and it's actually really, really nice. Another geometric feature that I added into this board is I designed a place for someone's foot to be. I wanted to make a cup for this linkage, so that someone's foot can actually sit in here and this be parallel to the ground. So I hope that they try and grind with it, and this kind of does its job. I think that's about it. And I'm really excited to see you make me skate it, break this thing, see where it breaks. My prediction is I'm going to have failures here and probably here, depending on how hard they land on it. I will recommend that they put Avenue suspension trucks on it to take some of the brunt of the force off of the deck to kind of give it the best chance of survival. But once they break it, I hope that they send it back and that I'll be able to really take a good look at it and then design another one and send it to them. Thanks for watching.